Hi everyone, in today's video, we will be going over contact versus non-contact forces. And also, we will be solving practice problems of forces in one dimension using free body diagrams. So first of all, let's go into what a contact versus non-contact force is. The definition is basically in the name. So a non-contact force is a force in which the two objects do not need to touch. For example, a ball falling towards Earth has the force of gravity exerted on it, but the Earth and ball don't need to touch such that the force of gravity is exerted on the ball. Gravity is a non-contact force. A contact force is where the objects do need to be touching. So for example, my hand has to touch this box in order to exert a force on it. Or another common force is the force of friction. So if the object was already moving with a certain velocity on a surface, a force of friction would be pointing the other way, or the opposite way of the direction of the object, and this requires contact between the box and the surface. So let's go over what friction is a little bit more. So you may have noticed when you slide an object on a surface with a certain velocity, it tends to slow down after a while. This means that there's some force acting on it, and this force is called friction. So most surfaces are not completely smooth. On a microscopic scale, surfaces are rough, so they have little ridges like so. On the microscopic scale, these ridges catch onto each other, and so a total net force will act in the opposite direction of the velocity of the object. This type of friction is called kinetic friction. And this means that the friction acts on the object when the object is moving. So if we were to say F stands for friction and the K stands for kinetic friction, the equation for kinetic friction would be F sub K equals to mu K and the normal force of the object. Remember that we went over normal force in the previous video. So what is mu K? Mu K is the coefficient of the kinetic friction for every surface. So, for example, if I slid an object on wood, it might have a different mu sub K. If I slid the object on steel, it would have a different mu K. So that means the friction for every surface would change if the normal force was constant. The second type of friction is called static friction. And static friction is the frictional force that is occurring between two surfaces that are not moving. So static friction keeps objects on inclines, or it keeps them from sliding. For example, if this person was pushing a block with a force of F, but the velocity of the block was 0, that means that there is a static friction exerted on the block from the surface that's also equal to Rf. This keeps the block from moving. So the way we represent static friction as an equation is F of static friction is less than or equal to mu sub s times the normal force of the object. So what this means is that for every surface, there is a maximum force that we can exert on it before the object starts to move. So if we exert a force less than mu sub s times the normal force of the object, it will not move because static friction will cancel that out, so our net force is 0. if our force was greater than mu sub n times normal force, then the object would begin to move. So you may see this if you placed an object on an incline, which we will go over in our 2D video. So if the surface has a certain mu sub s and a normal force of the object, then the static friction could be enough to overcome the force of gravity. And this prevents the object from sliding down the incline. It just stays stationary in its position. So that's what static friction is. It's the amount of force that is required to get an object to start moving. So let's represent this in a graphical way because sometimes static friction can be harder to understand. So this graph represents the friction force acting on an object as a function of our applied force. So we know that our static friction, or the maximum force needed to apply before it can overcome static friction, is mu sub s times the normal force. And in our graph, it's represented as 40 newtons. So as you can see, before 40 newtons, whatever applied force we have is matched with the friction force such that the net force is 0, so that there is no motion. So an applied force of 20 newtons, we get a static friction force of 20 newtons. Again, a net force of 0 and no motion. This continues until we reach 40 newtons. Once we pass this, our object begins to slide. And if we continue this force, no matter how much we increase the force, kinetic friction stays constant. Because once we slide, the kinetic friction is always equal to mu sub k times the normal force. And mu sub k is slightly less than mu sub s, so our friction force for kinetic, or for when the object is sliding, is going to be 30. And it stays constant despite our applied force. Question 2. A 7.5 kilogram cannonball leaves a cannon with a speed of 185 meters per second. Find the average net force applied to the ball if the cannon muzzle is 3.6 meters long. So we have the mass, and the mass is 7.5 kilograms. What we don't have is the acceleration, but we do have this information. We know that our initial speed is 0 because in a cannon, before shooting it, our ball is stationary. We know that our final speed is 185 meters per second, and we know that our displacement, which is the length of the cannonball, so the length the ball has to travel before reaching its final speed, is 3.6 meters. So I'm going to use the kinematic equation v final squared equals to v initial squared plus 2 times acceleration times displacement. I'm going to cancel out the initial velocity squared because it's 0. So to solve for a, all we have to do is v final squared divided by 2 times delta x gives us a. In order to get force, we have to do force is mass times acceleration. So our force net would be mass times v final squared divided by 2 delta x. So now let's plug this into our calculator. So our mass was 7.5 kilograms times a velocity 185 meters per second squared, and then divide all of that by 2 times our displacement, and our displacement is 3.6 meters. This gives us an average net force of 35,651 newtons. Okay, question 3 says, a stationary 2 kilogram object is located on a table near the surface of the Earth. The coefficient of static friction is 0.8 and the coefficient of kinetic friction is 0.65. If a horizontal force of 5 newtons is applied to the object, determine the following: a free body diagram, the force of friction, and the acceleration of the object. So, let's first start off by drawing a free body diagram. We know that our object is on Earth, so it has a force of gravity mg, and because it's on a surface flat, the normal force pushing up is also equal to mg. We are exerting a force, let's say to the right, of 5 newtons, and we have an unknown force of friction acting in the opposite direction. So let's first calculate our normal force so that we can calculate what our friction is. So our normal force is 2 kilograms times gravity, which is 9.8, and that gives us 19.6 newtons. Okay, so let's start off by calculating the maximum force we can apply before the object moves, and that is static friction. So calculating our static friction, we know it has to be less than or equal to the coefficient of static friction times the normal force. Thankfully, we have both of these. So our static friction has to be less than or equal to 0.8 times 19.6, which means that our static friction has to be less than or equal to, putting it in the calculator, 15.68 newtons. Since our force applied to the right is much less than 15.68 newtons, the force of friction that we get is going to match the force that we apply. So the force of our friction is going to be our static friction, and it's going to be 5 newtons, such that our net force is 0. If our net force is 0, then we know that our acceleration is also 0. So the acceleration of the object is 0 meters per second squared. Okay, this is our last problem. So the same information as before. We have a stationary object of 2 kilograms located on a table near the surface of the Earth. Coefficient of static friction is 0.8 and coefficient of kinetic friction is 0.65. This time, if a horizontal force of 16 newtons is applied to the object, determine the following: the free body diagram, the force of friction, and the acceleration of the object. So once again, we know that our object is on Earth, and it's stationary on a table. So that means there is a force of gravity mg and a normal force of mg, the opposite direction. Now we're going to apply a 16 Newton force. And this is going to cause a friction, we don't know if it's static or kinetic, in the opposite direction. So first, let's check if our force is greater than the maximum of the static friction. So we know that our static friction is the mu static, or the coefficient of static friction, times the normal force. And this is going to give us the maximum of static friction. So 0.8 times 2 times 9.8, which is 15.68 as we determined before. So as you can see, our force applied is greater than the static friction. That means that our object is moving and that the friction applied on the opposite direction is actually kinetic. So we have to figure out the kinetic friction. And the kinetic friction is 0.65 times our normal force, which is 19.6. And so our kinetic friction is equal to 12.74. 12.74 newtons. Okay, now we have our friction. So now we have to figure out a net force equation for the horizontal plane because our vertical plane already cancels out to 0. So F net equals to MA, which equals to 16 minus 12.74. So 16 minus 12.74 is going to give us 3.26. So this means that F net, which equals to MA, equals to 3.26 newtons. So we have our mass, so in order to figure out our acceleration, we have to divide our net force by the mass. So our acceleration is going to be 3.26 newtons divided by our mass of 2 kilograms. And plugging this into our calculator gives us an acceleration of 1.63 meters per second squared. Thank you so much for watching this video. I hoped it helped. And below in the description, I have linked a Google Doc of practice problems for all ranges of difficulty for forces. And in our next video, we will be going over how to calculate or do dynamics in 2 dimensions, which will be exciting. So thank you.